this video, I'm going to explain how to draw energy pie charts for different scenarios. So in your packet, if you turn to worksheet 1A, you will find a description of what you're asked to do. So in each of the problems below, you're going to use pie charts to analyze the energy changes in each situation given. The first thing that we have to do is decide what our choice of system is going to be. This means what objects are we going to include in our system, or as we said last class, which objects we are watching and monitoring the energy of. We want to try and make our system so that all the energy is internal, so it stays within the system and doesn't leave. We're going to create pies to correspond with the position of the objects given. And 3 questions, if you get stuck, are right here. Thinking about where energy comes from, where does energy go, and what does the energy do? So we're going to actually start by looking at number 2 together. So in this problem, a wind-up toy is wound up and moving across level ground. The toy is speeding up. So we can see that it's speeding up because it says so in the description, but also because all the arrows below the bunnies. So we see at the beginning, we have a really short arrow. At the end, it gets much longer. So we know that the velocity is increasing. Well, the type of energy that it depends on velocity is kinetic energy. So that means that we actually know that EK is going to increase throughout the pies. Now, I know there are 5 pictures here. In this case, I'm only going to draw 3. So I'm going to draw a pie for the first, middle, and last bunny, and think about what's happening with the energy. Last time we were in class, we also talked about where wind-up toys get their energy from, and that is from a person winding them up. So that then stores in the bunny what we refer to as elastic energy, because it's actually a spring that is wound up and tightened, the torsion spring within the bunny. So at the beginning, the bunny has a lot of elastic energy, but remember it still has some kinetic. So I'm just going to start by saying that it has mostly elastic energy and some kinetic energy. Now the actual proportion, if you do 3/4 and 1/4 or half and half, doesn't matter. What matters is what comes next. In traveling to my next pie, I need to make sure that my kinetic energy increases because we see that the velocity arrow is getting larger. So I need to have more kinetic energy here than I did before. And thinking internally about what's happening to the bunny, the spring must be unwinding. So the elastic energy in the bunny must be decreasing. Now, we had several other energy storage mechanisms, among them chemical energy, thermal energy, and gravitational energy. There's no change in height here, so gravitational doesn't seem to be involved. There aren't any chemicals. There's not a chemical reaction inside the bunny, so that doesn't seem to be involved. And thermal maybe, but I'm going to choose not to pay attention to that right now. So I need to just show that kinetic increases and elastic decreases. So I'm going to make my kinetic increase to half a pie, and my elastic decrease to 1/4 of a pie, or half a pie as well. So we see that that pattern has been followed. Now moving into the next pie, the same thing has to happen. Kinetic energy has to increase because we see a longer arrow for the bunny, and elastic energy has to decrease because inside the bunny, the spring is getting more unwound. So for kinetic to increase, I'm going to give it now 3/4 of a pie, and elastic will decrease then to 1/4 of a pie. So again, what we have to agree on when we talk about these pies are the pattern. Kinetic energy increase throughout the whole scenario, elastic energy decrease throughout the whole scenario. The actual breakdown of how much of energy was stored in each pie doesn't matter, but we have to agree on the pattern. Hope this helps. Good luck finishing up your homework.